The big question that we need to consider is why gravity can't work in a repulsive fashion as well. Things only gravitate. They don't seem to anti-gravitate. It's as though space can only curve in one direction, the direction that makes things attractive, not repulsive. In the 2D analogy, matter and energy only ever cause space to curve down, never up. And so there's only attraction, not repulsion. In the 3D grid analogy, matter and energy only ever cause those lines to be drawn inwards, never outwards. And again, there's only attraction, not repulsion. There's a profound and important reason for this that gets straight to the heart of what makes gravitation not only remarkable, but unique among the four fundamental forces. There's only one sign for the type of gravitational charge in the universe, a positive one. Think about that for a minute, because it's not typically the way we conceive of gravitation. We don't talk about gravitational charges. We talk about things like mass and energy when it comes to gravity. But of all the physical entities, both macroscopic and down on a quantum level, that have been demonstrated to exist, there's no such thing as negative mass or negative energy that's ever been discovered. Mass and energy overall must always be positive. Compare this up against a force like electromagnetism, and you'll immediately see the difference. When it comes to a phenomenon like electric charge, you don't just have one type of charge, you have two, positive and negative. Under the rules of electromagnetism, positive and positive charges repel, positive and negative charges attract, negative and negative charges repel, and negative and positive charges attract. In other words, the sign of the electromagnetic force, which direction the net force on each particle points, is dependent on whether the charges are alike, in which case they repel, or opposite, in which case they attract. The electromagnetic force, as it turns out, is much stronger than the gravitational force. If you put two positively charged protons close together and measured the repulsive electric force and compared it to the attractive gravitational force, you'd find that repulsion wins by a factor of about 10^36. So why doesn't the electric force dominate the universe instead of the gravitational force? The answer is that the universe is electrically neutral, where the amount of positive charge and the amount of negative charge balance out. Atoms are electrically neutral, with the positive electric charge of the nucleus exactly balanced by the negative electric charge of the electrons that orbit it. Planets, stars, and galaxies are predominantly made of atoms as well, and are electrically neutral overall. The reason the gravitational force is so important, arguably the only important force on extremely large cosmic scales, is because even though it's so tiny, it's cumulative. There's only one type of gravitational charge, and it adds up over time. The other two, nuclear forces, are also prohibited from affecting large scales. For the weak nuclear force, it's the fact that the force is mediated by extremely massive particles, the W and Z bosons. Because these particles are so much more massive than the particles that experience the weak interaction, these interactions are suppressed very strongly. It's only through the process of quantum tunneling from an unstable initial state to a more stable final state that the weak interactions can typically proceed. At greater distances, the suppression is greater, and so on scales greater than a subatomic particle, the weak interaction plays no role at all. For the strong nuclear force, the situation is a little more complicated. The strong force is mediated by gluons, and gluons are massless, like photons, which mediate the electromagnetic force. Unlike the gravitational force, which has one type of charge, or the electromagnetic force, which has two types of charge, the strong nuclear force actually has three types of charges that are all interrelated. We typically use a color analogy when it comes to the strong force, where red, green, and blue are the three colors. Cyan, magenta, and yellow are the three anti-colors, that a color plus its anti-color, red and cyan, green and magenta, blue and yellow, is colorless, and where three colors combined, red plus green plus blue, or three anti-colors combined, cyan plus magenta plus yellow, also makes a colorless combination. Only quarks and gluons have color among the fundamental particles, and the only states that quarks and antiquarks can exist in are colorless states. Baryons, 3 quarks, antibaryons, 3 antiquarks, mesons, quark-antiquark combinations. and more complex, shorter-lived states such as tetraquarks, 2 quarks and 2 antiquarks, and pentaquarks, 4 quarks and 1 antiquark, or 4 antiquarks and 1 quark. Because only bound, colorless states of quarks exist in nature, the force between any of these bound states must also occur through a colorless combination that conserves baryon number. Therefore, the mesons. Because all mesons are massive, this residual strong force, as it's known, is also short-range, just like the weak nuclear force. Gravity, however, is different. It is the force that governs the large-scale structure of the universe. From the formation of stars and galaxies to the overall shape and expansion of the cosmos, gravity plays a pivotal role. It is the architect of the universe, pulling matter together to create the cosmic web of galaxies we observe today. Without gravity's unyielding pull, the universe as we know it would not exist. Anti-gravity. On a fundamental level, true negative mass or energy states do not exist. The cosmological constant, which measures the effects of dark energy, tells us that the inherent energy in empty space is positive, small, but still greater than zero. There is no way to remove or subtract from this energy to achieve a negative value. However, we can manipulate space to create regions of lower energy compared to their surroundings. This creates an effectively negative energy region relative to the average mass energy state, but it remains gravitationally attractive, just less so than its surroundings. Antigravity will remain a fascinating mathematical curiosity. Although there are 4 known fundamental forces in the universe, there's only one that matters on the largest cosmic scales of all gravitation. The other 3 fundamental forces, the strong nuclear force, the weak nuclear force, and the electromagnetic force, are all largely irrelevant on cosmic scales. Why? The strong nuclear force holds protons and neutrons together. The weak nuclear force is responsible for radioactive decays and any species change among quarks and leptons. And the electromagnetic force causes neutral atoms to form. But when you gather large sets of particles together, these forces balance out at large distances. Matter, under these 3 forces, appears neutral at large scales, and no net force exists. But not so with gravitation. Gravitation is unique in this sense. With gravitation, there are only positive charges, things with positive amounts of mass and/or energy. Between those things, the gravitational force is only attractive, and so cumulatively, it can really add up. But why is it this way, and not any other? The answer lies in mass and energy. The gravitational behavior of the Earth around the Sun is not due to an invisible gravitational pull, but is better described by the Earth falling freely through curved space, dominated by the Sun. The shortest distance between 2 points isn't a straight line, but rather a geodesic, a curved line that's defined by the gravitational deformation of space-time. The notion of distance and time is unique for every observer, but under Einstein's description, all frames of reference are equally valid, and the space-time interval remains an invariant quantity. The more mass and/or energy you have in one place, the more space is curved by the presence of that mass and energy, and so the greater the amount that the fabric is deformed. For any object that moves through this region of space, the curvature of that space, the amount and direction that the fabric is distorted, determines how all entities, both massive and massless, will move through it. Now, a great many people will object to this. Because it depicts space as 2-dimensional instead of 3-dimensional, none of these things are true. Only, instead of a Cartesian grid, where all the lines are mutually perpendicular in all 3 dimensions, think of it as a grid where lines get sucked inwards by the presence of masses, as though someone grabbed a bunch of strings from a Cartesian grid and pulled them all in towards a single point. Now, let's venture into a fascinating hypothetical scenario. Is there any circumstance that doesn't require new physics, where we could actually observe or test the effects of gravitational repulsion? Are there any configurations we can imagine or create under which the gravitational force can be effectively negative instead of positive? Yes, you can design one. Instead of starting with empty space, imagine that space is uniformly filled with matter, like a massive, perfect fluid. Now, imagine that within this fluid, you have 2 types of particle to put down: a positive mass particle, whose density is greater than the density of the fluid, like a lead particle in water, and an effectively negative mass particle, whose density is lower than the density of the fluid, such as a solid-walled balloon or an impermeable aerogel in water. Under these circumstances, we can actually observe what's gravitationally attractive and what's repulsive.